Good afternoon. Thank you all for being here virtually and in person. I'm Rafael Akas. I'm going to present my work here. If you want to may follow the presentation by flashing the QR code or by the URL. So this presentation is about the security of distributed model predictive control under false data injection. Our needs shape the cities that we live today, but our needs change. And today we need smart ways to distribute electricity and heat, water. We want also to manage the traffic and many other problems that appear every day. So we have multiple systems that interact, and they may be coupled by constraints, such as technical constraints or comfort constraints of the users. And we may also have optimization objectives, such as minimize the energy consumption, maximize the user satisfaction, or just follow a trajectory. A solution is to use MPC. For those who don't know, MPC is the model-based predictive control, and the idea is to find the best control sequence using predictions based on a model. When I say best, I mean optimal. So we need an optimization problem, and we have as our decision variables the control sequence that are going to apply in the system. The control sequence is predicted using horizon M. So we need an object function to optimize the model of the system with its states and its inputs. And we can easily also add constraints that we want to respect, technical constraints or quality of service constraints. So if I give an example, if you want to follow a trajectory of temperature in a room, we have our set point and our state. We choose a horizon. You find an optimal control sequence and apply just the source elements of the control, and then we repeat this, and we have what you call a receding horizon strategy. But unfortunately, nothing is perfect. It has some problems. For example, this population problem can be hard to calculate. So it's the complexity of calculation. And the topology, the subsystems may be in geographical different places, and they need to interact. And another problem is the flexibility, because if you have just a block, it's difficult to activate and activate parts of the system. So we don't have this the flexibility to remove and add parts. And they also the part of the privacy, the confidentiality, because we have all the information just inside one box, and we don't want to exchange our information. So a solution is to divide the problem. It's what we call the distributed MPC. The idea is to take the MPC, break the population, and make some agents to communicate. As I said, break the MPC into multiple and make agents communicate. But how they communicate? There are many flavors to choose from. For example, we can use hierarchical analytic topologies, sequential, parallel, synchronous, asynchronous, bidirectional, unidirectional. There are lots of ways, but don't worry, you can see in the manuscript the description of this, and there are some examples in the distributed model predictive control mid-easy book. For this work, we choose these three kinds: hierarchical, synchronous, and bidirectional. That I'm going to explain next. As I said, you take the MPC and we break it into multiple MPCs and make them communicate. Here we add a coordinator to coordinate the exchange between the MPCs. So we have some kind of hierarchy. And we have this bidirectional communication because they coordinate the exchanges within the local agents, and the local agents can also exchange with the coordinator. And we don't, and we say that all this communication happens synchronously, there's no delays. So the idea is each local agent solves a local problem, and then the coordinator is going to update some variables until there's a convergence and a consensus between all these agents. Well, everything works fine if all the agents comply to play by the rules. But the problem is, what if some agents are ill-intentioned and want to attack the system? And so we raise the three questions that we're going to answer in this presentation. That they are: how can an agent attack the system? What are the consequences of an attack? And how can you mitigate these effects? So let's have a preview of what we're going to see in this presentation. about how the agent can attack. In the literature, these two articles, they present some attacks. As I said, the local agents, they solve an optimization problem. So we have objective functions, we have constraints, and the idea is to change internally these optimization problems. So there's the kind of attack there. You can change the objective function, you can change the constraint, or just change the control that is going to be used. And here you see what we call the deception attacks, because the agent wants to deceive all the other agents. But our approach is a little bit different here. We see from the coordinator point of view. And for the coordinator, what's important is just the interface, what he sees. So our idea here is that an attacker changes the communication between the local agent and the coordinator. And that the attacker ejects some false data inside the communication. That's what we call false data injection, and that's what you are interested in. About the effects, the consequence of the attack, we have our original optimization problem, and by attacking the system, the agent can change the optimization problem, and as a consequence, we can have a different optimal value. So we have another equilibrium. And to mitigate these effects, we can recover by ignoring the attack, and we change again the optimization problem. That's not very optimal for us. And the other way is to recover the original behavior, try to recover the original optimization problem, and have the equilibrium point close to the original one. And that's what we want to do here in this work. And if you want to classify the mitigation techniques, you can classify them either passive or active. And here I use the words robust and resilient. To make the difference in the robust, we have just one mode of control. In our classification, we say that we create our control, and we design the control robust enough so if there's an attack, we can still have some kind of optimality. And the idea of the active, we have two modes. One mode for when there's no attack, and another mode when attack is detected. So we need to detect the attack and also isolate to see what part of the system that attacked the system. And then we're going to mitigate the effects of the system by creating another mode of control. And we are interested in this part, the resilient part, the active. And if you compare what you're going to do with the state of art, you have here some articles. As you can see, the majority uses the dual decomposition and use a robust mitigation technique. And ours, we're going to use the primal decomposition and a resilient one. But if you compare with the other, instead of disconnecting the cheating agent, we are going to try to reconstruct some data to recover the original part. Okay. So to understand what we've done here, we divide this presentation in 4 parts. The first part, where I'm going to present the vulnerabilities of the decomposition that we're going to use. The second, where I propose resilient decomposition for some kind of system, which we call the private systems. And then we're going to relax some constraints and see there's going to be a module for the problem. And when we can circumvent this, and that's our mitigation mechanism. And then we end with the conclusion and some some future directions of the work. And here I'd like to point out that the first 2 sections here, they used a presentation in the CISCOL conference last year. And the third one, it used a conference paper in this year, next CISCOL. And this work was done with contribution with our friend Simon Leglet for the IMAC team that presented us an expectation maximization algorithm that I'm going to present in this work. So about the primal decomposition, I'm going to present the decomposition, its vulnerabilities, and the consequences of an attack in this framework. Primal decomposition, or also called point decomposition or resource allocation, has this flowchart as of the algorithm, the complete algorithm is there. But I'd like to explain that a little bit in a different way. It's like trying to divide a cake with different people. For example, a parent wants to divide the cake for the children. The parent is going to allocate a part of the cake for each children, which will say if they are satisfied or dissatisfied with the size of the cake. And then the parent is going to change the allocation for each of the children using by update function that depends on the previous allocation and the satisfaction of the parts, the children. And then, after some iterations, they are going to compromise and find something that is enough good for everyone. And then we apply mass control. In more detail, given you have an optimization problem, where we have objective functions, there are some of local objective functions, and we have some constraints that couple the variables. The idea is to take this optimization problem and divide it in multiple optimization problems, where we're going to allocate this variable theta for each agent. And each agent you're going to solve the local problem with this allocation, and they're going to send to the coordinator the dual variable lambda with the Lagrange dual, and there the coordinator is going to update the allocation by a gradient descent algorithm, but we still have to be sure that these global constraints are respected, so we project the set, so we have this projected subgradient algorithm. And then, if you have an example, here you're going to see the allocations they converge, and also the dissatisfaction they converge until everybody is equally dissatisfied. This is a negotiation. Okay. But how can a non-cooperative agent attacks in this framework? As I said, we are interested in the interfaces between the coordinator and the local agents. And the lambda is the only interface between the local agent and the coordinator. That's what he sends to the coordinator. So, as the lambda depends on the local parameter because it is the Lagrange variable, the idea of the attacker is to change this dissatisfaction that's going to be sent to the coordinator and use cheating function again. But how exactly does it does this? As I said, this lambda can be interpreted as a dissatisfaction. So lambda equals 0 means that this system is completely satisfied with the allocation given. So you have some assumptions here. The first assumption is that the attacker chooses one cheating function and it still uses this cheating function during all the negotiation. So it's fixed with the time. And another assumption is that the attackers say it is satisfied only if it really is. Mathematically, the cheating function will only be 0 if the original one, the satisfaction, will be 0. And another assumption that we make is that the attacker uses a linear attack. And by consequence of these two last terms there, we see that this attack is invertible. So there is a inverse of the matrix T. If I give an example, a unidimensional example here, we have our dissatisfaction lambda and our cheating function, and you'll see in the next slide that if we choose a linear function with a coefficient greater than 1, the agent will say he's more dissatisfied than he really is, and so he can get more resources. So here I give an example. Let's show this. We have 4 distinct agents, and one agent is non-cooperative and uses exactly the same expression that I said here, but with unidimensional coefficient. And here we make vary this coefficient, and we look at the cost of the local agents and also the global cost in blue here, and we can see 3 things here. The first is that the global minimum in blue the global in blue is minimal when we have this non-cooperative coefficient equals to 1. That means when there's no chipping. And other thing is that when agent 1 in orange, it increases this non-cooperative coefficient, you can see that its global its objective function decreases while all other objectives increase. So we receive more resource allocation. And another thing that we can see is that if he is too greedy, the system collapses because negotiation is not stable anymore. So how can we mitigate these effects that we just shown? And yes, at least in some cases. And the first case we're going to present is the case for the private system that we're going to explain next. And after analyze, we can create an algorithm and apply a mechanism to mitigate these effects. So what are the private systems? In one sentence, the private systems are systems whose optimal solution has all constraints active. If I give an example, here we have an objective function is constraints. And if you take a look at the constraint solution, we see that it's outside of the constraint set. So for the solution, we have this point outside. So we don't have enough resources, so the resources are scarce. So we can respond to the needs of the system. So the system is deprived. And then the solution is projected onto the boundary set of the set. That means that the solution is exactly the same as if it had equality constraints. So when we have scarcity, the constraints can be changed into equality constraints if the system can have all its constraints simultaneously. I can show you some examples that it's not true, but here we suppose that we can do this. So in our studies, we had some assumptions. We assumed that we have quadratic local problems, and they are deprived. There is some scarcity of resources, so we can use equality constraints. And as you know, the solution is analytical and affine for the U and also for the Lagrange dual. So we have this affine expression with P, which we as you see is time invariant, and with what we call the sensibility of lambda with respect to the theta, to the allocations. And we also have a constant value during the same negotiation, but it can change from time to time, which is time invariant depending on the states and other parameters of the system. And as I said, as we have confidentiality, the coordinator doesn't know exactly this parameter. So as I said, in the normal behavior, we have an affine solution of lambda with respect to theta. But when on attack, if the attacker reduces a linear function, we have new expressions for our satisfaction. So it's as like we change the parameters. But as I said, the P is not supposed to change. So we have a modified P, a modified sensibility. So the idea is if we see a change in this parameter that shouldn't change, so probably there's an attack. And we're going to take advantage of this to create a detection mechanism. So the first thing that we need for the detection mechanism is to estimate the sensibilities. And here we estimate the sensibilities and the constant value there using recursive list of squares. And there we assume that we can estimate the nominal value if we do this during an attack-free negotiation. And then we have the nominal value and the value that we just estimated, and we can compare them. And if they are bound, we say there's an attack. But exactly how can we estimate the speed, the sensibility? Just made the speed. We estimate using the recursive list squares, but there's a challenge. We can't do this during an online estimation. We can't do this online estimation during a negotiation because as we have an update function that couples the theta and lambda, we have what's called a low input excitation. So the solution is to increase the excitation for the estimation by sending a random sequence. And as you can see in the book Adaptive Control, random signal causes a persistent excitation of a non-neutral system. So idea is to, during a negotiation, the first step is we're going to excite the system, and then we're going to estimate our sensibilities, and then we're going to resume our negotiation. And as you can see, there's not the impact is not very big during this example. Okay, for our mitigation, active mitigation, we have our detection isolation, and now we need a mitigation. And how we're going to do this? As I said, we're going to reconstruct the signal. So we have the sensibility estimated, and we have also the expression of the modified sensibility by the cheating matrix, and then we can estimate the inverse of this cheating matrix by using this expression, and then we can reconstruct our dissatisfaction lambda by using this expression here. And then in our negotiation, we can choose adequately if attack is attacked, we can use the reconstructed lambda, and if not, we can use that was sent by the local agent. So the complete mechanism is just like adding a supervisor for each agent, where we're going to inquire the agent by sending random data, and we're going to estimate sensibilities. We're going to see how they will behave with the given allocations. And there we have two phases. The first to detect is one, the part where we send the random values, and then we're going to reconstruct the lambdas and resume our negotiation. And if I give the complete algorithm, you can see there are the two phases, the detection phase and the negotiation phase. And in the detection phase, as I said, I will be going to send random values until the RLS converges. And here we know that it will convert because we don't have any noise, and our attack is linear. So once the estimate of sensibilities converge, we can detect the attacker, and then we can resume our negotiation by changing the block where we update allocation by choosing which version of the lambda we're going to use the update. So here I give an example of this in Word. We have a distributed written network with 4 houses, different houses. Each one model we use on Amazon model. And we don't have enough power, so we can follow this trajectory. And we simulate using a period of 5 hours with 15 minutes in time. So we have 20 points of 20 steps in our simulation. And our prediction horizon is 4. And we simulate for 3 scenarios. The first one is a nominal one where there's no cheating. The second one where there's one agent that cheats, but we use the standard DMPC. And then another where it cheats, but we apply our safe mechanism. And here we can see the results. You can see in the air temperature in house 1 of the house of the attacker, and also the normal error of the sensibilities. In orange, you can see the selfish case, and then in magenta, the nominal one, and the black dots, the corrected one. And if you take a look, you can see that by looking at the normal error, we can see that the cheating starts at 6, and when the agent increases it, when the agent is selfish, it increases its comfort. If the orange line becomes close to the 20 degrees there. But when we can reestablish our behavior if you apply our safe DMPC. So you see the magenta the dots are close to the magenta one. And numerically, you can see the comparison of the objective functions of the local agents and the global. In the 2 cases, the selfish correct, we normalize the number 1. And you can see that when the agent 1 is selfish, it increases its optimality in 36%, while it decreases 3% of the global system. But when we apply our safe algorithm, we can see that we get very close to the original values. Okay, now I'm going to relax some of the assumptions that we made here, and you see how we can adapt to apply our mechanism. So relax the scarcity assumption. So our systems are not scarce anymore. Systems are not deprived anymore. Sorry. So we cannot change the constraints applied to us before. So we have to keep these constraints and also the updated equation. So for the solution for lambda, instead of having just one value of lambda, now we have multiple. We have what we call a piecewise defined function. We have lots of versions of the defined function, each one for one different region of where the location is, which depends on the combination of active and inactive sets or constraints. But still, we can take a look at the sensibilities and see that inside the same region, they are still in the time independent. If you want to analyze the regions, how does it work? Here we can have a simple example with just two variables, so you can see. And when there are constraints, we will have the different regions of the space. And the circuit will depend on the state, and it may vary from time to time. If we don't know exactly where one region starts and another ends. And they are on, as I said, they are not by the coordinator because it doesn't know the state of the system. But one thing that we know is that when you decrease the allocation, the systems become more and more deprived. That means when you have greater values of theta, our constraints are inactive, our lambdas are equal to 0. But as we get, as we decrease the values of the thetas, the allocations, we get more and more constraints that are active, until we have a region that we have all constraints active. That's what we are interested in, but unfortunately we don't know exactly how these regions determined. So the idea is to order these modes of the piecewise defined function in such a way that as we decrease the index, we increase the scarcity of the system. We make the system more and more deprived in such a way that the P0, when all constraints are active, they are exactly the same thing that we had seen before. And when none of the constraints are active, we have 0 because the solution is inside the constraint set, so it doesn't need to change the value. And here we make some assumptions. We assume that there is a region where all the constraints are active, and that we know one point, at least one point, that is inside of this region. That we're going to call the theta scarcity. Okay, but when the system under attack, as you can see, the parameters are modified, just as we made in the case. But here we see that there's no change on the region limits. So the idea is we can estimate the modified P0 that when all agents or the constraints are active, we can use the same strategy than before. The problem, as I said, we don't know the surface of the regions where they divide themselves, and the idea is to force them by using this point that we know. So artificial scarcity, you're going to use this point, the scarcity theta there, which activates all constraints. If we have some local constraints for the local problems, we're gonna also assume that this point also respects the constraint, so the problem is feasible. So we have a graph there with the multiple regions, and the idea is to generate points close to this theta. They are inside the region that you are interested, and then you're going to estimate the sensibility. It would be nice if you know the size of the radius, because we can pass from one region to another. And how do we know? We don't know. Unfortunately, we don't know. And the idea is to estimate it even if we don't know this radius. There enters the expectation maximization algorithm. There is going to help us there. And the idea is to, as the expectation maximization is an iterative method that estimates the parameters of a multimodal model. For example, the piecewise affine function, we have multiple affine functions. But we need to do some tricks so we can use this expectation estimation algorithm. If I explain what we're going to, how we are going to use expectation maximization and how it works, what to do, we send a lot of values of theta and lambda. And at each step of the algorithm, we're going to calculate the probability of each one of the zones having created this observation of lambda. And then we're going to update the estimates of these parameters by using these probabilities of each one of these observations that we had. And once the algorithm converges, we will have these parameters of sensitivity and mass associated with the region index, and also observation will be associated with these same region indices. And the idea is to consult the index associated to the theta restricted that we had, and then we're going to find the associated sensibility, and that's what we want. And once we have the sensibility, the P0 there, we can use almost the same ideas from before. We can estimate the nominal one if we have attack-free negotiation, and we having the nominal value of sensibility and the sensibility that we just found, we can detect an attack if it suppresses a bound, and also we can mitigate by estimating the inverse of the chip matrix. And then we can reconstruct our lambda by applying these inverse. So take a look at the complete algorithm. You also see the two phase, the detection phase, negotiation phase, but the difference here is how we calculate the detection phase. Now we're going to send multiple values of theta close to the theta restricted, and we're going to use the expectation maximization to calculate the sensibility, and then we're going to detect the self-attack and update the allocation using the reconstructed sensibility. And if we apply this in the same example here, we just change the set point and the state, so we can now have enough power, so the system is not completely deprived. We can see that in the selfish case, in the standard MPC, it also gets more resources. But when applying our new algorithm, we can still get back to the original behavior, and so the agent tries, but it can treat. And if you can compare also the numerical values of the objective function, we can see also that in the standard MPC it increases, but when we apply our corrected with the artificial scarcity, we can get very close to the nominal values. And here you can see that it's very close because we don't have any noise, and the shifting is linear. So it seems like magic to use the expectation maximization, but not necessarily. Unfortunately, we have some problems. For example, these method suffers for slow convergence, and it depends heavily on the initialization. So you have to get a bit close to the region of the perimeter so we can get a global objective. So there's no guarantees of achieving global outcome. Some of solution for these problems here One is to force some parameters to converge faster during the update of the expectation maximization, but it's very case dependent. And another solution, one solution for the dependency of initialization is to run multiple times. It's not like a solution, but it's what we see in the literature is to initialize multiple times in different places, and then we pick the best. And another way is to use associated with another method just to make initialization, and then use the expectation maximization once we have a good initialization. So here I show some of the conclusions of the work, and here we have some takeaway points of our question that we would like to answer. The first one, how can an agent attack? You can see that it can attack by changing the communication to receive more resources. What are the consequences of attack? Suboptimality and maybe instability. And how can we mitigate the effects? Can we mitigate the effects? Yes, by exploring the scarcity of the system. These are the takeaway. Then, if you want to make a quick recap of what we've done today here, from the analysis of the solutions of the optimization problems, we had two insights. The first one is the sensibility in their piece. They are constant when there is no cheating, and they change when there is an attack. And exploiting the scarcity of resources, the deprivation of the system, we can invert the attack. It is straightforward if the system is completely deprived, but if not, we can try to artificially make the system deprived. But as you see, the problem is it has a piecewise defined solution, and we need some estimation, special estimation method to estimate what we want. And now the great question is, what if the complete scarcity information is not available, not even artificially? And then we have some future directions of how to exploit this. And the first one is to try to reconstruct the cheating matrix by using partial scarcity. When the constraints, all the constraints are not active, so it takes just the active constraints and try to reconstruct the matrix. This is one point. The other point is try to study the robustness of our methods and with error propagations, and also how it behaves when there's noise during the communication. Another way, or the future direction, would be to use a resilience strategy. This resilience strategy, but with different kinds of constraints. For example, when we use a quality of service constraints where the constraints are relaxed. And another thing that we can use is to try to, instead of having a block of detection, try to detect it during the negotiation by using some kind of recursive algorithm. And many other questions that are still open. So everything is available in the GitHub repository. And if you want to contact me, you can also send me an email. And I'm here, open to questions and comments, and thank you all for being here.